This video review that I wanted to go over with you comes from one of the notes handouts that are from the Sapling website, and it looked very good with some very good pictures on it, so I thought it would be useful to include this in my group of videos. So it just goes over some of the basics of gas laws, and it had some pretty good pictures with it. This first one here we see is Boyle's Law. Right, Boyle's Law is a relationship between pressure and volume, and this is the equation we've been using for Boyle's Law. But I wanted you to have a good visual of what's really happening with Boyle's Law. It's when you're keeping temperature constant, but you're changing either volume or pressure in a container. So if pressure is allowed to change, then that can be moving this depressor here, this top part of the container, so that you can see that the amount of volume, the amount of space that the gas is allowed to be in changes. So if we push this down, then the volume decreases. If it's allowed to expand, then the volume increases. So that visually gives you an idea of when we're looking at the relationship in Boyle's Law between pressure and volume, but we're not changing temperature. So we could take temperature out of the equation. In Gay-Lussac's law, we're looking at the relationship here between pressure and temperature. So that means volume is staying constant. That's the gas law that we would use if, say, for example, a word problem specifically said it was in a rigid container. Something like a steel container where it's not allowed to expand or contract, where we're just looking at the impact of pressure changes and temperature changes. And along with that, you have a good picture here of the temperature scales. Just another way to make sure that you're able to do a calculation back and forth between Celsius and Kelvin. For practical purposes in a laboratory, often temperature is measured in Celsius. It's the type of thermometers we have, for example. But in the gas laws formulas and many scientific formulas, Kelvin temperatures have to be used because all of the numbers are positive and it's measuring from absolute zero upward. So everything is in relationship to your 0 point of absolute zero. Charles' law is when we're just looking at the relationship between volume and temperature. How does volume vary or change as temperature is changing? So in this case, pressure is held constant. For example, that's the idea behind how a hot air balloon works. They heat up the gases, which then those gas molecules spread out, become less dense, and therefore it's lighter than air, and the air balloon is allowed to rise. Avogadro's law is not one that we included directly in this particular unit, so I'm going to skip past that one. The combined gas law is sort of your one-stop shopping for gas laws, where you've put together pressure, volume, temperature in your initial conditions and your final conditions. I have excluded from this particular unit including moles in this calculation also. So we've been using P1V1 over T1 equals P2V2 over T2 and just keeping number of moles the same. And then the last gas law that we're covering in this unit is the ideal gas law. The ideal gas law starts out with the premise that we're more or less pretending that the gases in this situation are perfect. They obey the kinetic molecular theory perfectly. Remember, some of the tenets from the kinetic molecular theory are not 100% accurate, but they are assumptions that are made if we say that our gas is ideal or perfect gas. For example, that there's no force of attraction between the gas molecules would be an assumption that's not exactly true. So, with the ideal gas law, this is the formula: PV equals nRT. Pressure times volume is equal to the number of moles times the gas constant R times temperature for any gas that is obeying the kinetic molecular theory. R value is a corrective value. It's a constant. There's many types of many constants throughout science that have to be in a formula to make the two sides of the equation equal. We used one earlier this year when we used Planck's constant earlier this year. So R value has to be here to make both sides equal. But remember, there's several different R values to choose from because we do use different possible pressure unit systems. So if we use atmospheres, you have to use this number. If we're using kilopascals, this number. Millimeters of mercury or torr, either one would be 62.4. And then Dalton's law of partial pressures is one of the gas laws that I eliminated from this particular unit. I also plan to post this actual document in there for if you wanted to print it for any, for your notes, etc. But I thought this was a great additional resource to have as you prepare for the upcoming test.